All right. Good afternoon, everyone, and welcome to this session. In this session, we're going to use software evolution to not only identify, but also to prioritize technical debt. So let's jump right in and see what this is all about. And my starting point here is Martin Fowler's well-known definition of technical debt. And I want us to focus on the key aspect here. And the key aspect is that technical debt, just like its financial counterpart, incurs interest payments. And I've found that this is something that we in the software industry tend to misuse and sometimes even misunderstand. And the consequence is that technical debt, the concept, is not as useful or helpful as it could be. Let me show you what I mean about that. And the way I want to show it is by having you do some work. I want to do a little experiment. So what's going to happen now is that I'm going to put up a piece of code here. And your task is to judge the quality of that piece of code. Are you ready? Here we go. Have a look at this wonder. How many of you think that this is excellent code? How many would let it through in a code review? Really, just me? Oh, I got a companion too. Now, of course, this is not the kind of code we want. It's not good code, right? And of course, we would never ever do something like that ourselves. Never ever. But is it a problem? Is it technical debt? Without more context, we just cannot tell. Because technical debt, it isn't technical debt unless we pay an interest rate on it. An interest rate is a function of time. So that means, to answer if that is technical debt or not, we need a time dimension into our code. Where can we get such a thing? Well, in a few minutes, I'm going to show you one way. But before we go there, I would like to share a little story with you. So, as part of my day job, I go to different companies and I analyze the code bases and I try to come up with some recommendations and improvements. And last year, I visited a company that prior to my arrival had used a tool capable of quantifying technical debt. So they had taken this tool and threw it at their code base. And this tool reported that on your 15-year-old code base, you have accumulated 4,000 years of technical debt. 4,000 years. Just to put that into perspective, 4,000 years ago, that was here when Moses parted the Red Sea. So, in this case, it may well be accurate, but it's not particularly helpful. I mean, given 4,000 years of technical debt, where do we start? How useful is that? In addition, I think it's a mistake to try to quantify technical debt from code alone. And the reason I say that is because most technical debt isn't even technical. And again, this is something I find over and over again, that we as developers, we tend to mistake organizational problems for technical issues. And the consequence is that we treat the symptoms instead of the real disease. So you may have come across example of that. Let's say that you come to a new company and you hear someone say that, hey, watch out with this part of the code. It's really hard to understand and I never can make sense of it, right? Or to make it a more obvious example, perhaps you heard this one, that yeah, we spend a lot of time merging our different feature branches. We need to buy better merge tools. As you will see, there may be an organizational side to both of these two problems. And I think the main reason that we keep making misattributions like this is because the organization that builds the system is invisible in the code itself. And this is unfortunate because there is a strong link between technical debt and organization. And we cannot address technical debt unless we take a holistic view of the concept. And that holistic view has to include a social view of our code base. So, based upon what I have told you so far, I put together a wish list, kind of a list what we would need in order to prioritize technical debt. So, let's walk through it. First of all, we would like to know, where's the code with the highest interest rate? The second thing we would like to know is, if we look at architecture, does it support the way our systems evolves? Are we working with or against our architecture? And the final point, and perhaps the most important one, is are there any productivity bottlenecks for inter-team coordination? You know, those parts of the code where 5 different teams have to work together all the time and need to coordinate all the changes. So please have a look at this list and think back to the project you work on right now. Is this information that you think could be useful to you? I see that some of you nod. That's a good sign. The interesting thing, though, is that none of this information is available in the code itself. In particular, we lack 2 pieces of really critical information. First of all, we lack that time dimension. And second, we lack that social dimension into our code. So how can we get those? Where's our crystal ball? It turns out that you all already have one. We're just not used to think about it that way. I'm talking about a version control system. Let me show you an example. You see a simple piece of a Git log here. Our version control system is an informational goldmine. Because when we look at version control data, we get that time dimension. And even so, we know in what order the different changes happen, and we can use that to calculate statistics and frequencies, as I'm going to show you soon. But even more important is that version control data is actually behavioral data. It's social data, because our version control system knows exactly what programmer that did what change at what point in time. So let's embrace version control data, and let's see how it helps us identify code with the highest interest rate. And the concept I use to identify code with high interest rate is something I call hotspots. So let me show you an example of how that looks. So this is a hotspot analysis of a well-known Java codebase, Tomcat. Has anyone worked with Tomcat? Yeah, a lot of you. Cool. So Tomcat is a old and mature system, right? And I'm going to walk you through the visualizations so that you know what you see. First of all, this is a hierarchical visualization that follows the folder structure of your code. So if you see those large blue circles that blink there on screen, each one of those represents a folder. And you have subfolders inside them, right? Other large blue circles. And it's also an interactive visualization, which is important once we get to larger code bases, so we can zoom in to the level of detail we're interested in. And when we do that, you will see that each file is visualized as a circle. And you see that the circles have different size. That's because the size of a circle is used to represent the code complexity of that file. So how do we measure code complexity? Well, we have a bunch of different ways to choose from. We have things like McCabe's cyclomatic complexity, we have Halstead's volume metrics, and what all of those have in common is that they're equally bad. So basically you can choose any metric you want. It's really just an estimate, right? So I tend to recommend the simplest thing that can possibly work, and that's, in this case, it's actually the number of lines of code, which has a strong correlation to the other metrics. So let's use that as our complexity metric. But that's not even the most interesting part. The interesting part here is the change frequency of each piece of code. And this is data that we can pull out our version control system and use that as a proxy for interest rate. So what we want to look for here is the overlap between these 2 dimensions. We want to look for complicated code that we have to work with often. And that's our hotspots. So let's return to Tomcat here. And you see that in Tomcat, the hotspots, there are in relatively few areas. And now, just because something is a hotspot, that doesn't mean it's a problem. A hotspot just means that this is where most of the development activity is. So those are the parts of the code that requires extra attention. Those are the parts of the code that you want to keep clean, simple, and as easy as evolved as possible. However, in practice, more often than not, I tend to find that the opposite is true. So hotspots tend to make up excellent refactoring candidates. And there's a fascinating reason why that's the case. And I want to explain that to you by borrowing a sentence out of George Orwell. Because I have found that while all code is equal, some code is more equal than others. Now, what do I mean about this? Well, let's have a look at this graph here. What you see now are 3 graphs that all show the same kind of data. So let me walk you through this. First of all, you see the x-axis here. It shows each file in the system, and those files are sorted according to the change frequency. That is, how many commits have you done to each file. And the number of commits is what you see here on the y-axis. Now, the interesting thing is, if you look at these three systems here, they're from completely different domains, developed by different organizations. There are different developers behind them. They have different lifetime span, different programming languages. Everything is different. And yet, do you see any similarities in the pattern? That's right. They all show exactly the same thing. They show a power law distribution. And this is something I've found in every single system that I've analyzed. And I've been analyzing more than a couple of hundred systems just over the past year. This seems to be the way that software evolves. And this is important because it gives us a tool to prioritize. Because what this means to us is that most of our code is here in the long tail. It's code that we rarely, if ever, touch. And a small percentage of our code is here with a very, very high change frequency. And that's the part we want to focus on. And that's the part that hotspots help us identify. Now, hotspots make up a really good starting point for refactorings, but sometimes they are not enough. And I want to show you one example on that by switching to a different case study. Are there any .NET programmers in the audience? Yeah, some of you. So let's see if you recognize this one. This is the .NET Core runtime from Microsoft. And the .NET Core runtime is quite fascinating. It's a large piece of code. And when I did this hotspot analysis, I think it was 6 months ago, it turned out that most of the hotspots are here in the JIT package, the just-in-time compilation. But we also see that there's another hotspot here, kind of a satellite, something called gc.cpp. That's the .NET garbage collector. Now, gc.cpp, it looks quite innocent on that visualization, doesn't it? But that's just because the scale of .NET Core. gc.cpp is huge. How big? I have no idea, so let's look it up on GitHub. It's turned out to be a pretty good capacity test, right? So it's too large to visualize with syntax markup. So we need to look at the raw file. And when we do that, we find out that gc.cpp consists of 37,000 lines of C++. Now, 37,000 lines of C++, let me tell you this. I used to be a C++ developer. I did C++ for 10 years. And yeah, I know what you think, right? That's 10 years I never get back. And that may be true, right? But at the same time, 37,000 lines of C++, I cannot even imagine how scary that is. And in addition, how helpful would it be to learn that gc.cpp is a hotspot? So let's say that I come to your organization and say, hey, look, I found your biggest technical debt. If you just rewrite this file with 37,000 lines of C++, all the problems will go away. Again, it would be accurate, but not particularly helpful. And besides, how do we act upon information like that? The answer is we don't. We need much more details. So what I suggest is this. That once we find those big hotspots, what we do is that we run exactly the same analysis, but now on a function and method level. So we basically parse that large file, and then we'll look at what parts are hit, what functions are hit by the different commits, and look for trends in that. Let me show you how it looks on gc.cpp. So when we run a hotspot analysis on gc.cpp on its functions, it turns out that the number one hotspot on a function level is a function called grow brick card tables. It's a function with 332 lines of code. It's quite a lot for a single function, isn't it? But it's much less than 37,000 lines of code, which was the size of a total file. And it's definitely less than 4 million lines of code, which was the size of a total system. So more important, we are now on a level where we can act upon the information and do a focused refactoring based on data from how we actually work with the code. So we're going to come back to the hotspots, but before that, I would like to know, how can we get to a file with 37,000 lines of code? You see, I just can't let that go. So let me introduce to the best book I know on how organizations fail. This is a book called The Challenger Launch Decision, and it's written by Diane Vaughan. And it's interesting because Diane Vaughan isn't a software developer. She's a sociologist. So she investigated an organizational hypothesis that she had called Normalization of Deviance by using the Challenger disaster as a case study. So how many of you remember the Challenger accident? So like 1/3 approximately. So let's do a quick recap on this. This was more than 30 years ago. And what you see here is the Space Shuttle Challenger on its final journey. And the large white object that you see here, that's something called a solid rocket booster. And do you see this puff of gray smoke here? It's not a good thing. It's not supposed to be there. So what happened here during the Challenger was that those solid rocket boosters, they are huge, huge rockets. And they are delivered in 3 different segments that are assembled before the launch. And it turned out that one of the joints in those 3 segments simply leaked. So hot rocket gases were able to escape and had an impact on the structure of the spaceship. So it simply disintegrated. Now, the interesting thing with the Challenger is that, as Diane Vaughan writes in her book, back in the 70s, when they did the early tests upon the design, it turned out that the solid rocket booster joints didn't perform as expected. They had a deviation. Now, what do you do when you find something like that? Well, if you're NASA, you form a committee. So they did. And they discussed the problem and passed it off as an acceptable risk. Years later, during the first in-flight tests of the space shuttle, again it turned out that the solid rocket booster joints deviated from the predicted performance. Again, the problem was discussed and passed off as an acceptable risk. And it went on and on like that for years, before, even on the very eve of the final launch, there were some concerns raised by some of the engineers due to the unusually cold temperatures in Florida at that time. And again, it was discussed and passed off as an acceptable risk. And the consequence was a tragic loss of lives and a spaceship. So this is what Diane Vaughan calls the normalization of deviance. Each time you accept a risk, the deviations become your new normal. And I find this interesting because it's not about spaceships. This is about people. And we have plenty of normalization of deviance in software development too. So let's say, for example, that you inherit a file with 5,000 lines of code. That's quite a lot. But if you work with it long enough, those 5,000 lines of code are going to become your new normal. And I mean, besides, what difference does it make with a few extra 100 lines of code, right? So soon you have 6,000 lines of code. Then you have 7,000 lines of code, and so on. So we need to find a way to stop the normalization of deviance. And the first step is detection. So here's one technique that I've been using for that purpose. This is something I call complexity trends. So what I do here is that I take all my main hotspots, and then I pull out the historic revision of each one of them, and then I measure the code complexity at each point in time and plot a trend like this. So what you see here are actually 2 lines. The blue line is the growth in lines of code, and we see that yes, it does increase. And the red line is one of the complexity metrics. And we see that it increases even more rapidly. And using this data, we can read the whole history of this file. We can read and uncover its evolution. And we see that sometime here early last year, there was a focused refactoring, but that refactoring failed to address the root cause, and soon the complexity keeps creeping back in before there's a recent and very steep increase here. And this is definitely a warning sign. And the normalization of deviance is one of the reasons why whistleblowers are so important to an organization. And I have found that complexity trends make great whistleblowers in code. So to sum this up, using hotspots, we can identify the code with the highest interest rate. And the reason they work is because all code isn't equal. We tend to spend most of our time in a relatively small part of the code. And that's where we want to prioritize improvements, because that's where we get the biggest return on investment. And we've also seen how complexity trends may help us detect if we approach the normalization of deviance. Now, I want us to climb up the abstraction ladder and talk about architecture. And as you know, you cannot really talk about software architecture without mentioning art. Does anyone recognize this? No one. That's good. Because this is the artist Gustav Metzger and his liquid crystal light projections. And the fascinating thing with that stuff is that it's alive. It changes all the time, right? So this artwork looks completely different today than it did yesterday. And the interesting thing is the way it changes. Because a change here necessitates the destruction of an existing form for the creation of a new form. And I like that, because that's exactly how code is supposed to evolve. It's also the reason that I like hotspots, because they kind of make it clear that the codebase is never done. Successful code evolves, and that's a good thing. The reason I say code is auto-destructive is because in many systems, changes and new features tend to become increasingly more difficult over time. And some systems, they just reach a tipping point, and beyond that point, they get extremely expensive to maintain. So we could use the hotspots to try to detect that tipping point, but in a large system, we want to operate on a higher conceptual level. We want to operate on the level of logical components and architectural elements. So let me show you how that's done. The first thing we want to do here is to move from files to components and subsystems. And the way I do that is that I basically just group different files into a logical component. So in many architectures, you may map individual folders and all their content to a particular component. And then I just aggregate all the code and aggregate all the contributions to that part of the code. And now I can run a bunch of different analyses on that level. And once we do that, we can start to answer a lot of interesting questions, because we can start to reason about how our system evolves on an architectural level. And I want to show you how that's done. And I want to show you by introducing a concept called temporal coupling. Has anyone heard about temporal coupling? Yeah, some of you. Great. So this is how it works. In this simple case, we have 3 different subsystems. And we notice that the first time we make a change to the system, we modify the fuel injector and diagnostics module together. The second time we make a change, we modify something else. And the third time, we're back to modifying the fuel injector and diagnostics module together. Now, if this is something that a trend that continues, there has to be some kind of relationship between the fuel injector and the diagnostics module, because they keep changing together all the time, right? So this is something we can use to uncover the change patterns in architecture, how we as a development organization actually work with the code. And I want to show you a number of examples from 2 different architectural styles. And I want to start with the layered architecture. And the reason I want to start with layers is because it's so incredibly popular. And it's used by many legacy systems. So as part of my day job, when I come to different organizations, and I always ask them, what kind of architectural style do you have? And when they answer layers, they usually say something like, we have a model view controller, or a model view presenter, or a model view view model, or whatever, right? The interesting thing is that that's never how the architecture really looks. Because we all know, if you work with a layer architecture, let's say these are the 3 classic MVC parts, we know that we need more layers than that, right? Because we know we need a services layer for all that application logic. And of course, we also know that we need a repository layer. And the reason we need a repository layer You see, I never came up with a good answer to that one. So let's just call it a best practice. And of course, below that, we want an object relational mapper, and then because we don't want to access the SQL directly, and then maybe we have some SQL at the end. And in many architectures, you have even more layers. You may have things like view helpers and so on. So the interesting thing now is that if we run this architectural analysis I've been talking about, what I would do now is that I would take all code that belongs to each component here and aggregate the contributions to that code and look for patterns. And if I do a temporal coupling analysis on that level, my change patterns will look like this. In fact, I have found that somewhere between 30 to 70% of all commits touch multiple layers. So most of your commits basically ripple through your architecture like this. And this is interesting because one of the main motivations behind layered architectures is a separation of concerns. However, what actually happens is that few changes become local. So most of our changes we have to modify all those parts, and the reason for that is because a layered architecture like this separates along a technological axis, while the work you do is feature and problem oriented. So it may well be that we have a separation of concerns, but perhaps it's the wrong concerns we are separating on. And layers as such may work really, really well in a small team. It may be a good starting point. However, it's really hard. The consequence of those change patterns is that it's really, really hard to scale it and make it work for a large organization. Because if you think about the consequences here, what actually happens once you get more people into that architecture is that everyone will work in every part of the code. And that puts you at risk for not only increased coordination needs that we're going to talk about soon, but also things like unexpected feature interactions, which are incredibly hard to track down. And I think that this kind of issues may be one of the driving points behind the recent popularity of microservices. And as we all know, this is exactly what microservices look like in PowerPoint. In reality, we know that they are much, much more complex, right? We know we have shared building blocks, we have service templates, we have client APIs, and we have cross-cutting concerns like monitoring, diagnostics, and so on. And the challenge with microservices is that in a microservice world, loose coupling is king, right? So the moment we start to couple different services to each other, we lose most of the advantages of a microservice architecture, and we are left with an excess mess of complexity. That's not what we want. So when we have a fundamental principle like that, why don't we supervise it? So what I would do here is, again, I would start to measure a temporal coupling on a service level. And in particular, I would look out for change patterns like this that crosses service boundaries. And I will use that as an early warning system to catch and investigate potential problems early once you start to couple services logically to each other. And if we do that, we're able to avoid problems like what I call the microservices shotgun surgery pattern. Now, the microservices shotgun surgery pattern is basically this idea where you want to tweak a single business capability and you end up modifying 5 different services. And the reason that happens, there are several reasons, but the ones I've seen are the most common ones, are first of all that the different services, they may share code that itself isn't stable from an evolutionary point of view. So changes to shared code ripple to other services. It may also be the case that services are leaky abstractions. And once they expose their internals, other services will depend upon them. And you have coupled the lifetime of different services to each other. I've also seen that this is much more common when the same team is responsible for multiple different services. Perhaps because it becomes so easy to just start to send directed information, which is also kind of a leaky abstraction. All right, what kind of tools do I use to do this kind of analysis? There are several options. When I started out, And when I started to work on my book, Your Code is a Crime Scene, there weren't any tools available that could do the kind of analysis I wanted to do. So I put together my own tool suite and I open sourced it. It's still available. I still maintain it. Did the last change just a couple of weeks ago. So it's called CodeMath, available on GitHub and completely free and maybe a good starting point if you just want to play around with these ideas. What I work on right now is something called CodeScene. And CodeScene is all this analysis as a service. So please check it out at CodeScene.io. It also has a bunch of different showcases of well-known open source projects that you can investigate. Then there are also a bunch of interesting tools in the academic world. And my personal favorite has to be the evolution radar, which is particularly strong on temporal coupling. So have a look at that one. Finally, if you want to write your own tools, which you should, it's really fun, then I recommend that you look at the Moose platform, which is a framework for writing code analyzers, basically. Moose is also a perfect excuse to learn to program in Smalltalk. It's a wonderful language. All right. So I haven't showed that, but the hotspots, we learned how we can pull up the analysis to an architectural level, and we can run a hotspot analysis on that level too if we want. We can also use temporal coupling to supervise architectural principles and reason about the cost of change. Now I want to spend the final minutes of the presentation on exploring the social side of our code. So before I do that, I would like to ask you, how many of you develop software as part of a team? So that's like virtually everyone, like 90% of you. Yeah, we have to do that, right? Because we take on larger and larger problems and our code bases become larger and more complex for every single year. So we need to get together. We're not able to do it ourselves anymore. And it's interesting, though, that most of us work in team, but we're rarely aware that teamwork always comes at a cost. And this cost is something that social psychologists call process loss. And process loss is a concept that the psychologists borrowed from the field of mechanics. And the idea here is that just like a machine cannot operate at 100% efficiency all the time due to things like friction and heat loss, the same is true for a team. So let me illustrate that. Let's say we have a bunch of individuals here, and together they have a potential productivity. However, that's never, ever what you get out of a team. The real productivity is always smaller. And part of the potential is simply lost. Now, the kind of process loss that you get depends upon the tasks that you do. But I would claim that in a complex domain like software, most of the process loss is simply due to communication and coordination overhead. And the bad news are that you can never eliminate process loss entirely. The trick is, of course, to minimize it. And I'm going to show you one more specific example of process loss, and then we will see what we can do about it. So this is another concept from social psychology called the diffusion of responsibility. And it's a common cause of process loss. So now, the diffusion of responsibility, it's something you can witness in the real world if you're unfortunate enough to witness an accident or an emergency. Because it turns out, the more people that are present, the less likely that any individual will offer help. That's actually quite scary, isn't it? So if you're in an emergency situation, it's better to have 1 or 2 people there than 200. It's really scary. Now, what does that have to do with code? Well, we have a lot of diffusion of responsibility too. And this ties into quite a controversial topic. This is the kind of topic you're not supposed to speak about. You shouldn't even mention it. But I think I need to do that anyway. I'm going to talk a little bit about code ownership. Yeah. And I just want to make clear that when I say code ownership, I don't mean ownership in the sense that, hey, this is my code, stay away. No, not at all. I mean code ownership in the sense that someone takes a personal responsibility for the quality and the future of that piece of code. And that someone could be an individual, it could be a pair, it could be a small pair in a large organization. Because I'm pretty convinced that we must feel that our individual contributions make a difference. And good code is code where you have a sense of personal responsibility from everyone involved. There's really no way around it. So if we have an important principle like the diffusion of responsibility, how can we detect that? How can we measure that? Well, remember, we are in version control wonderland. So we know exactly which developer that has worked where, so we can simply look for an overlap in development activity and map that to our file structure. Here's what it looks like. So this is the same kind of visualization as we used earlier, only now the color signals a different thing. The color signals parallel work. So the more red a file is, the more people have worked and contributed in that part of the code. And we can use that to detect those areas of the code that need our attention from an organizational side. And the bad news here are that once you detect those parts of the code where you seem to have a high diffusion of responsibility and lots of parallel work, it's usually quite hard to do something about it. But you still need to act because it turns out that the number of developers behind a piece of code is one of the best predictors on the number of defects you will find in that code. It's a pretty well-researched topic. So what do you do once you find code like this? Well, first of all, take a look at it from a technical perspective. Because most of the time, code changes for a reason. So the reason a piece of code attracts many different programmers is probably because it has good reasons to do so. It has too many responsibilities. So look for opportunities to split it and separate the different responsibilities. Try to build higher cohesion, which is not only good from a design perspective, it's also something that helps you eliminate a lot of the coordination overhead. Another thing that you want to do is you want to look at it from an organizational perspective. And it may turn out that your organization may lack a team. So you may actually have to introduce a new team to take on a shared responsibility. And this is something I find to happen all the time in things like this, integration tests. We tend to be a collaborative effort, and it usually pays off to have someone kind of own that part of the code and take the responsibility for what comes into it and how it evolves from a quality point of view. Now, using version control data, we can do a lot of more other stuff to explore the social side of our code. We can actually measure things like Conway's law. So let me show you a quick example on that. Same style of visualization, but now each color represents the contributions of a team. So we group individuals into teams and look at where do they work in the code. And you see an example here on this is a package by feature architecture. And you see that from the perspective of Conway's law, this looks absolutely wonderful. Right? Each team have their own dedicated part of the code where they can work in complete isolation. That's wonderful. No coordination overhead at all. It's also a lie, right? It's a lie, and I have to do a small confession here. All visualizations of data that you have seen so far are from real-world systems, except this one. Because I haven't found an organization that's actually that well aligned with their code, and I'm not even sure that that's the way to go. I think this is a step too far for separate reasons that I can talk about after this session. It's actually a talk in its own. So let's instead look at a more typical finding. This is from a real code base. It's a system I analyzed a couple of months ago. And what happened here was that this was an organization that decided to introduce feature teams. So they took their existing organization and split it up in 12 different feature teams. And they worked in sprints, and at the start of each sprint, every team was assigned a bunch of tasks, kind of a round-robin mechanism, and then they were let go on the code base. So this is what their contributions looked like after 1 month. And you have to look a long, long time at that to start to see some patterns. I mean, sure, there's 1 or 2 parts of the code that's maybe almost not really in the hands of a single team. But most of the time, what you see here is basically a communication disaster. This is collective chaos. And it's collective chaos because you have 12 teams that work in the same parts of the code all the time for different reasons because they work on different stories. Not only is this really, really expensive to coordinate, it's also problematic since you miss synergies between different features. That is, you miss opportunities to make simplifications to both the problem and the solution domain. So please, no matter what you choose, align your architecture and your organization. Your code is going to thank you for it. So I hope you enjoyed this journey through the fascinating field of evolving code. And ultimately, it's all about writing better software. Software that can evolve with the pressure of new features, novel usages, and changed circumstances. And writing code of that quality will never be easy. So I think we need all the support we can get. And I hope that this presentation has inspired you to investigate the field in more depth. So before I leave time for questions, I put together a number of links here if you want to read more on this. I have 2 books about the subject, Your Code is a Crime Scene, Software Design X-Rays. I also blog about it, and I have a bunch of different case studies on my blog here at mpr.com. So, before I take some questions, I would like to take this opportunity and say thanks a lot for coming to my session, thanks a lot for attending, and may the code be with you. Thanks.
We have 5 minutes before lunch, so you could ask questions. Raise your hand.
Yeah. Also, remember afterwards, I have a bunch of Code as a Crime Scene stickers, so come forward and grab one.
A quick question about this. You mentioned that it is not really a good thing when many people, more than one, works on some part of the code, right? What about like extreme programming and shared code ownership? Like people seem to constantly work on the entire code base, changing like pairs on any piece of the entire product. So does it? Oh, it has proved to work, right? If you agree with that, so how to align both those statements? Thank you.
Yeah. So I think the key thing here to keep in mind is that the context is always important, right? So when I talk about individual programmers, I'm not talking about practices like XP or even mob programming. I think when you want to do this kind of analysis in an XP or a mob context, you don't want to look at individual contributions. You want to consider the team, the unit of analysis. And a team should always carry a meaning from an architectural perspective, no matter what development practices you use. So my recommendation in that case is to just skip the individual level because you have practices to deal with that and look at it from the perspective of the teams. Hope that makes sense. Any other questions? Or are you hungry?
So the question is about the organization and architecture. So when teams are tied to particular modules or architecture, then it usually makes some big stories to implement quite problematic. So product manager or project manager needs to work with multiple teams, like 2, 3, 4, 5 teams to make something done. And project manager never, it's like hard to get status of each piece of work. So do you think it's, how can it be solved?
Oh. If I knew exactly how to solve that, I wouldn't be here because I would be rich. So I've been thinking about it a lot, right? And I've been doing a lot of work in that area. I have separate presentations about that. There are 2 things. First of all, yes, you do need ownership, right? But that ownership has to mean something, not only for the team, but also from the problem feature side of your architecture. So I think most of the most serious problems, they occur when you have that technical organization of your code. And it's not, I know I've been bashing about layers, but I see exactly the same thing happening now with microservices. that a lot of organizations, not a lot, but some organizations start to build microservice systems that are oriented around technical capabilities. And I'm pretty sure that I don't think that will scale from the organizational point of view, because you will get all those coordination bottlenecks anyway, only now it's distributed. So I'm pretty sure that no matter what you choose, you need to align your architecture with the way your domain works. That's the only way to go. And you want the team to be capable, even if they're not able of working the whole stack, they should at least be aware of it. So I think it's important to distinguish between what I call operational boundaries, that's where the team works right now, this part of the code, from the knowledge boundaries, which has to be much broader. So we actually need to, if you have an interface to another team, we need to know a bit about their code and their situation, and we need to know the people there. And there are several practices you can use to make that happen. For example, the next time you call a code review, make it a practice to invite someone from the teams that uses your piece of code. And it's also something that helps limit a lot of social biases. Like you probably heard about the fundamental attribution error, right? Where we make a we and them distinction. That's also, so practices like that may help to limit that. So I think that's really, really important to keep that distinction in mind.
Thank you.
Lunchtime.
Thanks.